In section 14.2, we look at Euler paths and Euler circuits. City, including garbage collection, sweeping, and snow removal, have been scheduled and organized using graph models. By determining efficient routes for snowplows, garbage trucks, and street sweepers, cities are able to save money each year. Such routes must ensure that each street is serviced exactly once without having service vehicles retrace portions of their route. We have seen that a path in a graph is a sequence of adjacent vertices and the edges connecting them. Recall that an edge can be part of a path only once. If a path passes through each edge of a graph exactly one time, it is called an Euler path. An Euler path is a path that travels through every edge of a graph once and only once. Each edge must be traveled and no edge can be retraced. So for example, in the diagram below, we're going from A to B. We go from B to E, E to F, F to D, D to B, B to C, C to E, E to D, and D to G. We can see that the path is not a circuit because it does not start and end at the same vertex. If an Euler path begins and ends at the same vertex, it is called an Euler circuit. An Euler circuit is a circuit that travels through every edge of a graph once and only once. Like all circuits, an Euler circuit must begin and end at the same vertex. So we're going to just copy and paste the same graph from above, but the only thing is that we added an extra edge between G and A. But again, we only hit every edge once. So we go from A to B, B to E, E to F, F to D, D to B, B to C, C to E, E to D, D to G, and G to A. So we started and ended at vertex A. Every Euler circuit is an Euler path. However, not every Euler path is an Euler circuit. Some graphs have no Euler paths, other graphs have several Euler paths. Furthermore, some graphs with Euler paths have no Euler circuits. Euler's theorem is used to determine if a graph contains Euler paths or Euler circuits. So Euler's theorem says the following statements are true for connected graphs. If a graph has exactly two odd vertices, then it has at least one Euler path, but no Euler circuit. Each Euler path must start at one of the odd vertices and end at the other one. If a graph has no odd vertices, or they're all even, then it has at least one Euler circuit, which by definition, it also has an Euler path. Because every circuit is a path, but not every path is a circuit. An Euler circuit can start and end at any of the vertex. If a graph has more than two odd vertices, then it has no Euler paths and no Euler circuits. So looking at example number 1, explain why the graph has at least one Euler path. So using Euler's theorem, let's go ahead and figure out if it's got an Euler path, an Euler circuit, or none. So that means we need to look at the degrees of all of our vertices. So let's look at A first. A has two edges, which means this is degree 2. B has 4 edges, so that's degree 4. C has 4 edges, so we have degree 4. D has 3 edges, and E has 3 edges. So now looking at our degrees of all our vertices, we know that A is even, B is even, C is even, D is odd, and E is odd. So let's look at Euler's theorem. If a graph has exactly 2 odd vertices, which is what we have, that means it has at least one Euler path but no Euler circuit. So by number 1 in Euler's theorem, the graph has at least one Euler path but no Euler circuit. Then we want to use trial and error to find one such path. So by the Euler's theorem, it says that it must start at one of the odd vertices and it ends at the other one. So we have to start at either D or E and end at the other one. So let's go ahead and start with D. This is just going to be by trial and error here, but the goal is to hit every edge once and only once. So starting at D and ending at E, I am first going to move to C. Now from C, I have a few different options. I can move to B, I can move to A, or I can move to E. I am going to move from C to B. From B, I have a few options. I can move to A, I can move to D, or I can move to E. So I'm going to move to E. From E, I have two different options. I can move to C or I could move to D. I'm going to move to C. From C, I only have one option. I can move to A because I've already moved across that edge to B. So I have to move up to A. And from A, I can only move to B. From B, I only have one choice left, and that's to move to D because the other edges have already been used. And from D, I'm going to end my path at E, and that is one Euler path. There are going to be other ones in here, but that is the one that I found by trial and error. Let's go ahead and try another one. A little bit more complicated of a graph. We want to explain why the graph has at least one Euler circuit. So same thing as last time, I want to write all of the degrees of the vertices. So A is degree 2, B is degree 2, C is degree 4, D is degree 4, E is degree 2, F is degree 2, G is degree 2, G is degree 4, H is degree 4, I is degree 2, and J is degree 2. So every single one of these is even. So what does Euler's theorem say about this? So by number 2, because we have no odd vertices, it means it has at least one Euler circuit. So by number 2, the graph has at least one Euler circuit. And we want to use trial and error to find one such circuit. So by Euler's theorem, it says that we can start and end at any vertex. So I'm just going to pick H. It does not matter which one you start at. There are going to be multiple circuits in this one. So starting at H, we have a few different options. I'm going to go from H to G. And remember, because this is a circuit, we need to start and end at the same vertice. So from G, I'm going to go to E. And from E, I'm going to go to C. From C, I am going to go to D. From D, I'm going to go to F. From F, I'm going to go to H. From H, I'm going to J. From J, I'm going to I. From I, I'm going to G. From G, I'm going to go to C. From C, I'm going to A. From A, I'm going to go to B. From B, I'm going to D. And the last one is D to H, which closes off my circuit. And that, again, is only one of the circuits that is in this graph. There are other ones. The figure above shows a graph with one even vertex and 4 odd vertices. Because the graph has more than 2 odd vertices, by the third statement, it means it has no Euler paths and no Euler circuits. Just as a side note for the previous one way we can write this instead of just drawing on the graph is by writing the letters in order that I'm hitting them. So it would be like H to G, and then we went from G to E, and then E to C, C to D, D to F, F to H, H to J, J to I, I to G, G to C, C to A, A to B, B to D, and then we finished off as H. We can use Euler's theorem to solve problems involving situations modeled by graphs. For example, recall the graph that models the layout of Königsberg shown below. People in the city were interested in finding if it were possible to walk through the city so as to cross each bridge exactly once. In graph theory, we are interested in whether the graph has an Euler path. Count the number of odd vertices. There are 4 odd vertices. Because the graph has more than 2 odd vertices, it has no Euler paths. Thus, there is no possible way anyone in Königsberg can walk across all the bridges without having to recross some of them. Below shows the work we developed to model the connecting relationships in a floor plan. Recall from our work in section 14.1 that A, B, C, and D represent the rooms and E represents the outside of the home. The edges represent the connecting doors. Is it possible to find a path that uses each door exactly once? So we need to look at the degrees of all of the vertices. So looking at A's got 4. B has 3. C has 4. D has 3. And E has 6. So using Euler's theorem, is it possible to find a path that uses each door exactly once? Since we have 2 odd vertices, which are B and D, that means that this has to have at least one Euler path. So the answer is yes. By number 1 in Euler's theorem, the graph has at least one Euler path. But no Euler circuit. If it is possible, we want to find a path. So we have to start at one of the odd vertices and end at the other one. So let's go ahead and do this starting with B, which means I need to end at D. So starting at B, I'm going to move outside to E. From E, I'm going to go back inside to room A. From room A, I'm going to B. From B, I'm going to go to D. From D, I'm going to go to C. From C, I'm going to go to E. From E, I'm going to go to A. From A, I'm going to go to C. from C, I'm going to go back out to E. And from E, I'm going to go to D. And so writing this out the long way with the letters, I started with B. I went outside to E. From E, I went to A. From A, I went to B. From B, I went to D. D, I went to C. C, I went to E. E, I went back out to A. From A, I went to C, which then went back to E. And E went to D. Again, that's only one of the paths. There can be other ones. Euler's theorem enables us to count a graph's odd vertices and determine if it has an Euler path or an Euler circuit. Unfortunately, the theorem provides almost no assistance in finding an actual Euler path or circuit. So we have an algorithm to help us with this process. If Euler's theorem indicates the existence of an Euler path or Euler circuit, one can be found using this procedure. If the graph has exactly two odd vertices, and therefore an Euler path, choose one of the two odd vertices as the starting point. If the graph has no odd vertices, and therefore an Euler circuit, choose any vertex as the starting point. Number the edges as you trace through the graph according to the following rules. After you have traveled over an edge, erase it. This is because you must travel each edge exactly once. Show the erased edge as a dashed line. When faced with a choice of edges to trace, first choose any edge that is not a bridge. Remember that a bridge is an edge whose removal would make the graph disconnected. Travel over the bridge only if there is no alternative. So this figure has at least one Euler circuit, and we want to find it by using the algorithm we just talked about. So the instructions tell us that this has an Euler circuit, which means there are no odd vertices in this graph. And we can begin at any vertex. A lot of times we just choose A to start. I'm going to do each step in a separate graph so that you can see the transition and the thought process behind all of it. So starting with A, we have a few different choices. We could go to D or we could go to C. We just need to make sure that neither one of these edges is a bridge. Because if one of them is a bridge, then we want to make sure we choose the other one. We only choose the bridge if there is no alternative. So if I were to move to D, I'd still be connected to other points. And if I move to C, I'd still be connected to other points. So it doesn't matter which one I move to, I am going to move to D. So I erase the line, and I'm just going to put a little line so that I know which way I'm traveling. So now that we're sitting at D, we need to see which ways we can move. I have a few different choices. I can move to F, I can move to B, or I can move to C. Again, we want to make sure that none of these are bridges before we choose them. So if I move to F, I would still have points that I'm connected to. If I move to B, I would still have points that I'm connected to, and the same thing with C. So let's just go ahead and move to C. So now that I'm sitting at C, we have some options. I can move to A, F, or E. Again, we want to make sure that none of them are bridges. But if I were to move to A, I would be stuck at the vertex with nowhere to go because all of the edges are already erased. So I can't move to A. So that leaves me with F or E. I just need to make sure that either one isn't going to cause any issues, which they don't look like they're going to, so we can go ahead and just move to F. Now that we're sitting at F, we have three options. We could move to D, we could move to B, or we could move to E. If I move to E, the only place that I could go is C, and C goes to A, which means I have not hit the other edges on the left side of the graph. So that means I can't move to E because this would then strand me on the other side with no way to get back. So that leaves me two choices. I can move to D or I can move to B. Let's go ahead and move to D. Well, now that we're sitting at D, we only have one choice. I have to move to B because there's no other way for me to go somewhere. And now that I'm sitting at B, I only have one place I can go, which is F. From F, we only have one place to go, which is to E. And from E, we only have one place to go, which is to C. And from C, the last place that I can go is to A, which is exactly where I wanted to end up. So this means that my final circuit goes from A to D, D to C, C to F, F to D, D to B, B to F, F to E, E to C, and back to A.